starting point. Let me call it S to be my starting point. Okay, S will map to S. And when I take the square root of that thing, I make sure that theta equal to 0. Okay, so that this point maps to that point. As I march along here, it's slowly increasing theta from 0 to something. Then what I would do is that as I increase theta from something, then I will map to something like 45 degrees. If that's 45 degrees, this will be 22.5 degrees. Okay, as I march along, I will see that this is been going like that. Okay, and this thing is the square root of this length over here. So if I keep marching to 90 degrees, then it will map to 45 degrees over here. So I'm still on the top Riemann sheet over there. I keep marching. Okay, if I go beyond 90 degrees, they will go beyond 45 degrees over here. And then if I keep marching until I hit the Great Wall of China, then I will hit 90 degrees over there. This is how the mapping goes. So I've completed marching around the top Riemann sheet. Now I'm about to cross over to the left half plane. And over here, I encounter this branch cut. At the branch cut, I have two choices. I jump over the Great Wall of China, or the branch cut. If I jump over this branch cut, I would jump from here to here. It's like a great leap forward. Okay, great leap across the complex plane. Okay, but if I decide to go below the branch cut, okay, I will keep myself on this left half plane. And if I keep marching, let me call this point A, and that point will map to A over there. Okay? And then if I keep marching over here, I'm on the left half plane. Let me denote this with solid lines. Okay? And if I decide to go to the left half plane, I actually have to go to the bottom Riemann sheet, which I denote with a dotted dash mark. Okay? And then when I reach over here, I'm actually over here. Now, but on the bottom Riemann sheet, let me see, is that right? I'm just over here actually. Just over here. Just over here. And then when I go over there, okay, I should be over here. Okay, S prime should map to S prime, but on the bottom Riemann sheet here. Okay? And then I can keep marching, but I'm on the bottom Riemann sheet now. I'm on the bottom Riemann sheet now. Okay, and keep marching on the bottom Riemann sheet. And then I keep marching until I hit the Great Wall of China again, okay, over there. And then I'm just about to leave the bottom Riemann sheet. If I cross this line, I'll go to the top Riemann sheet. Okay? So over here, I'm encountering this branch cut. I have a choice of jumping over the branch cut. Okay? Because I'm on the bottom Riemann sheet, I can go above, under the branch cut, and emerge to the other Riemann sheet. Okay? I can emerge. You can think of the branch cut as something like this. I was on the top sheet. I can jump over here. I can go to the bottom Riemann sheet. This is bottom, top, top, bottom. So I was marching on the bottom sheet, and when I encounter it again, if I want to maintain continuity, I should go through a smooth transition from the bottom to the top in this manner. I can jump across like this. I will jump Riemann sheets. Okay. So if I do that, then I will emerge to the top again. The second time I encounter the branch cut, then I will map from here to here. And then I will go back to S again. Okay, meet up with S. So that's how roughly the mapping goes. Another way of thinking about it is that if I march in the clockwise direction, I will go along this line and backtrack and get to this point B. This point B is actually this point there. Okay, we go in the backtake direction. B and A are actually very far apart on the complex F plane, but they are just next to each other on the complex Z plane. But they're actually topologically very far apart because there's a branch cut there. Okay, if you jump over this branch cut, you jump from A to B. If you creep under the branch cut, okay, if you're on the top here, you go under the branch cut, you go from B to here. There's a point next to it. Okay? And the same thing goes, if you're on the bottom Riemann sheet, if you just click across it, you go to the top Riemann sheet. But if you jump to the different Riemann sheet. Okay, is this clear? What the branch cut and the Riemann sheet is. If you have had a course in complex variable, maybe you know, right? If not, then you actually have to think about this. Okay? So this is how roughly the mapping goes. And we distinguish and do the bookkeeping with the branch cut. And then everything is well defined. Okay? So we use the same technique to keep track of the function kz. Kz is undefined or uncertain due to the fact that we can have plus or minus choice over that. And so one way is to find, since we always want imaginary kz to be larger than 0 for our integration, for a Sommerfeld integral, okay, let's try to find where the imaginary kz line is. Imaginary kz equal to 0 line is. Okay, and if you can find where that line is, maybe you can use it as a branch cut to distinguish between the upper Riemann sheet and the bottom Riemann sheet. Okay, how do we find this line where imaginary kz equal to 0? So we let k rho be a complex number, okay, having a real part and imaginary part. K rho squared then will be k rho prime square minus k rho double prime square plus 2I k rho prime, k rho double prime, right? So kz is equal to the square root of k0 square. We can let k0 be a complex number as well, k0 prime plus I k0 double prime. Okay, and then minus k rho square would be equal to minus k rho prime square plus k rho double prime square minus 2I k rho prime, k rho double prime. So in order to find out where imaginary kz to be 0, we want this argument here to be real, completely real, so that it take a square root, it doesn't have any imaginary part. So how can we ensure that this is completely real?
That should be k naught plus I k naught double prime whole square.
Oh, square. That's right. You are right. Square. Okay, so this should be square. So how should I do that? It should be replaced with something that looks like that. Oh, I'm sorry. Thanks for pointing that out. So it would be k0 prime square minus k0 double prime square plus 2I k0 prime k0 double prime. Okay, so the whole integrand, the whole argument will look something like that. Don't you agree? Sorry for the mess up. I want to make sure that this square root always gives me a pure real number so that its imaginary part is equal to 0. So the imaginary part must cancel each other. So one condition is that k0 prime, k0 double prime is equal to k0 prime, k rho prime, k rho double prime. This is one condition. Okay. The other condition is that this real number over here must be less than this real number over here. So k rho prime square plus k rho double prime square must be less than or equal to k0 prime square minus k0 double prime square. If these two conditions are satisfied, then the imaginary part of kz would be real, would be 0, sorry, and the argument in there would be purely real, right? Real and positive. Real and positive. This makes it real and positive, things make it purely real. Okay, but what do these two equations mean? The first equation is of the form of xy equal to a constant. The second equation is of the form x squared plus y squared is equal to a constant. Constant 1, constant 2. So what do this?
That should be a minus.
Where is this minus?
Minus
K 0 double prime squared, right?
K row double prime square. It should be K row prime square minus K row double prime square less than the second.
Oh yeah. Yeah, you're right about that. Yeah. Okay? So this should be, you're correct, okay? This should be, what do these two equations conjure up in your mind? Xy equal to constant is a? It's a rectangular hyperbola, right? The second one is just a hyperbola. So if you plot these two equations on the complex plane, if I just plot it on this quadrant, the first equation, if this is K row double prime, K row prime, okay, the first equation is just a line something like this. Okay, and it passes through this point. K0. Okay, if that point is there, okay, it passes through that point over there. Okay, the second equation actually looks something like this. It's also a rectangular hyperbola, but rotated by 90 degrees. This is this equation. This is that equation. Okay, you will check those equations. And then this inequality says that if I pick my branch cut to be here, if I pick my branch cut to be that part of the two lines here, then this would ensure that imaginary kz is equal to 0. And that is my imaginary kz equal to 0 branch cut. Okay? But it turns out that this mapping is two-way. You can also show that k row is equal to k0 squared minus kz squared. So for every value of kz, there also are two values of k row. For every value of k row, there are two values of kz. And you can go through this argument and discover that there is a minus k0 point here. And there's another branch cut that goes like that, which is just a mirror image, not exactly a mirror image, the counterpose of that other branch cut. So those are the two branch cuts that you should have. Okay? That you should have. I think we have to stop here. And these are called the Sommerfeld branch cut. So everything got named after Sommerfeld. Sommerfeld branch cut, Sommerfeld integral, Sommerfeld identities, Sommerfeld lots and lots. Okay? So he somehow is equivalent to winning the Nobel Prize. So there's the Sommerfeld half-plane problem, there's the Sommerfeld Watson transform. There's lots of things, so you should be happy.